लग रहा था कि ये
Uh, Good morning, everyone.
Morning, sir.
Uh, okay. Uh, I need, there is two clarifications basically. One is regarding the tutorial one. How many of you solved this question 9? Have you guys tried to solve question 9?
Yes, sir. Sir, in tutorial 1 or tutorial 2?
Tutorial 1.
Yes, sir.
It matched with my answer. What is the answer that you got?
सर ये जब मैंने सॉल्व किया था तो इसका जो डेल ऑपरेटर निकाला था हमने उसमें सर आई कैप वाला जो अपने एक्स कंपोनेंट है वो 0 आया था सर।
Now,
तो अपना
what is
अपने
the final answer?
सर फाइनल आंसर आपके वाले से मैच नहीं किया मेरा।
Who else? What is the value you got?
So, -1.
Uh-huh. Other people? You guys should try to solve, whoever is not solving, okay? But yes, my answer was wrong. That is, you guys are right. The answer should be -1. Okay. Answer should be -1. My answer was wrong. But whoever is not solving these questions, you guys should try to start solving, okay? Google Classroom, you who else? Alok यादव
सर
क्यों नहीं आया है?
सर सर क्वेश्चन नंबर 11, 13 और 17 में सर डाउट था मेरे को।
This doubt you should ask on Thursday.
ओके।
What you were present on Thursday class or not?
यस सर।
Which question?
क्वेश्चन नंबर 11।
Question number 11 we have solved that day, right? What was question 11? Question 11 I told you, you are not present.
नो
That's why
सर, आई एम प्रेजेंट ऑन दैट क्लास।
we told you how to solve question 11.
कैन यू प्लीज एक्सप्लेन वन मोर टाइम?
We'll tell again on Thursday, next lecture.
हिंट कर।
we showed you how to do this del operator. Okay, who don't have no tutorial 2 and tutorial 2 will discuss on Thursday. Yes, tutorial okay, there's another problem is that some of you emailed me this one. Question number 5 on assignment. Assignment question number 5, this value should be 1/3. I told you to prove that the vertical deflection is half omega g t cube sine lambda. This should be 1/3 omega g t cube sine lambda. Okay. It's on the question number 5 on assignment. Okay, let me okay, before going there, let me paste whoever don't have the Google Classroom. I'm posting in this chat. You guys join through this, okay? This is the link for Google Classroom, okay? You guys can join. Whoever has not joined yet, you can join using this link. Yes, you have to submit assignment in the Google Classroom. And yeah, okay, let me share the screen. Tutorial set 2 will discuss on next Thursday. Okay, this question this question number 5 on assignment. It's I told you to prove that omega g t cube sine lambda deflection. This is wrong. It's correct should be 1/3 omega g t cube sine lambda. Okay. Someone emailed me. So who is that? Who emailed me? Arin Agarwal. He emailed me question 3. Yeah. If you guys find any mistakes in the assignment, in the final formula or in the answer, you guys can tell me, okay? Sometimes there can be some mistakes, but you guys, if you guys solve this problem, then only you know that this is mistake and you should email me. And whoever is not solving, you guys should start. Otherwise, you guys will be in trouble.
So,
Okay, any other question?
sir, regarding the assignment,
Yes.
so for the 5th question, I am facing some problem in solving the question. So, where to refer for the particular theory of the question?
You can check this Goldstein book or any classical mechanics book. It's generally solved. Wherever this Coriolis force is discussed, you can check there.
Okay, sir.
Okay, any other question? Okay, if not, then let's continue. So in the last lecture, we were
Hello, sir.
yes,
Sir, I am Sasi Kamal. Sir,
yes.
my admission was done on spot on. Then how I proceed or continue my study? Kindly explain me.
Yeah, so I have sent you the necessary links. Basically, one is for this online class is this Zoom link, and we meet on this Zoom link every day. Okay, this link is fixed. We meet on the same link. And second thing is that I also send you how to join Google Classroom. You join there. So we have so far how many lectures? 5 or 6 lecture. Okay. And all these lecture recordings and lecture notes you can find on the Google Classroom. And there is some also problem set. You can those are also problem set and answers. Those are also uploaded on the Google Classroom. So you start checking those online videos and notes, okay? And if you face any problem regarding those, then let me know. So whatever we are starting from yesterday or from tomorrow, this will be quite independent of what we have discussed so far. Okay. So you should not have any problem in understanding the next lectures. Okay. But
Okay, sir.
for question answer purpose and exam purpose, you should check out this previous lecture notes and videos. If you face any problem, you let me know. Okay.
Okay, sir. Thank you, sir. And sir, I didn't do any assignments. Then I can do later.
So we already have one assignment that is due for Friday, 30th of August. Okay. So if you can solve, it's okay. But if you can't, then also it's fine. I'll consider this special case. Okay. But you check, those are based on vector calculus. So if you can solve, it's fine. But if you can't, then also it's fine. You check whether you can do it or not.
Okay, sir. I will try my best to solve the assignment. Okay, sir. Thank you, sir.
Okay, so let's recap what happened so far. So
Excuse me, sir.
basically,
I have a doubt
yes,
in the assignment. Can you please tell the solution of question number 2 in the assignment?
assignment, no. Those we have to solve first. No,
मतलब आप एक बार उसको क्वेश्चन को थोड़ा चेक कीजिए ना क्या
no.
क्वेश्चन सही है क्या?
I will only give the questions. Solution I'll only ask after you guys submit, not now. That's why those are assignment. I will not ask.
I'm just asking to just check the question, not I'm not demanding the solution, whole complete solution.
What is assignment 1? Assignment 2 is very simple. I told you to do A dot grad R that is equal to A. No, these
But
are not discuss anything. This is simple thing. We should try to do. We will not discuss anything.
is that question right?
What is question 5 also? I see.
Not
I
not
gave
5,
you the
not
basic theory
not
of.
5,
I gave
not
you
5
the basic
question.
theory of Coriolis force and those things. And based on that, you guys should try to solve. Okay. We'll not discuss.
I'm
Only after you guys submit this thing, then only we can discuss.
I'm talking about question number 2, not
भाई
5.
सही है क्वेश्चन
I
नंबर
told
2
you
सही
question number 2 also will not discuss now. This is a simple question. It's simply written in English. You guys should try to solve. I'm not giving you any hint for this.
Okay.
I checked who have this Google Classroom. I just sent the link couple of chats back. You check. It's in the already posted in the chat. How to join this Google Classroom. Okay. So let's continue. So we are studying this motion of system of particles. System of particles. Okay. And we are deriving basically the kinetic energy and the potential energy. We showed how to how to tackle this system of particles and what happens if external force acts on the system of particles. So we told you that if you have a system of particles, let's say this is a system of particles and you have some n number of particles here. And each of the particles are located at Ri and the position, let's say at Rj and so on. And each have mass, let's say Mi and Mj. And we told you that if some external force, Fe acts on the system of particles, then it feels like that the whole force is acting on the center of mass. As far as linear momentum is concerned, we have seen that the linear momentum is basically as if the whole force Fe that acts on the center of mass at A, and we have seen then the linear momentum can be constant. And similar thing we have also seen for angular momentum as well. And then we are trying to determine the kinetic energy and the potential energy of the system. So for kinetic energy, for kinetic energy, we showed you that let's say this is the position of Ri and this is position of R, And the position of the ith particle from the center of mass, that I told you Ri prime. And then I told you that you can write Ri is basically R plus Ri prime. And then if you do derivative of this, then you will get the velocity. This will be equal to velocity of the center of mass plus velocity of the ith particle with respect to the center of mass. No, sorry. This should be Vi prime. And then we tried to derive the total kinetic energy of the system. Total kinetic energy of the system was simply half mi Vi square. And we replaced Vi by V plus Vi prime. And then we got the final answer was like something like half m v square plus half mi vi prime square. And that means this first term, this is basically the kinetic energy of the center of mass. Kinetic energy of center of mass. And the second term, this represented as if the particles, motion of the particles around the center of mass. And these were kinetic energy appearing because of the motion of the particles around center of mass. So you can separate these two terms as far as the kinetic energy is concerned. And now we should also be able to determine the potential energy. And we will do similarly as far as the single particle was concerned. That the total work done was basically 1 to 2, and the force whatever was acting on the particle, and that is F(phi) dot dri, and if we take the summation over all the particles. This was the total work done, right? Sorry, this should not be Fi. This is the total force acting on the particle Fi. And we know that Fi has two components. Fi is basically Fie plus Fji. That the external force acting on the ith particle and the internal force acting on the ith particle due to all other particles present in the system. So this we have also discussed at the beginning of the lecture for the system of particles. Okay. So if we replace Fi by this term here, what we'll get here? So we'll get this summation will be outside I, and we are moving from 1 to 2. And what is Fi? We replace this Fie plus J for, let's do the dot product here. Let's do the dot product dri. Okay. And also then we'll have two summation for ij, where j not equal to I. That was important. I told you that the same particles we need to discard. Okay. And this will be 1 to 2 Fji dot dri. Okay. Now we can evaluate this term separately. Okay. Only when the forces are conservative. Forces are conservative. And I also discussed what is conservative force. So that when force is conservative, then we write them as V equal to the minus gradient of V. Then we can call these forces are conservative. Okay. So we can try to evaluate the for the first term. Okay. So let's try to find out what happens for this term. 1 to 2 Fie dot dr. Okay. So let's see 1 to 2 Fie dot dri. Okay. So if forces is conservative, then we can write Fi in terms of some gradient function. So let's say we write this as gradient of I V I, okay, dot gradient of V dot D Ri, okay. And this will be, if you do this integration, it will be 1 to 2 D Vi, and this will be equal to Vi 1 to 2. And you can do this summation over all the particles also. You can do this summation over all the particles. And this will minus Vi, summation over I. So this is the basically the first term, okay. And you can again do the similarly, you can do the second term, okay. We are not going to do the second term. You can try to do. So for the second term also you can write Fji. This should be equal to gradient of some function, gradient of I Vij, gradient of I Vij, and we also know that Fij this should be equal to minus Fji because of Newton's law that if jth particle is exerting some force on the ith particle, then ith particle will also exert same and equal force on the jth particle. And so this should, you can also write gradient of J V Ji. Sorry, this should be gradient of J V Ji. And if you do this if you replace this Fji by this gradient of Vij, then you can work out the second term as well. Okay, you can work out the second term, that I comma j 1 to 2 Fgi dot dri dot dri. Okay, and this term you can show, and this term will be equal to minus half Vij. This term will be equal to minus half Vij and summation over I and j. Okay. So then the total potential energy will be this term plus this term. So then you can write the total potential energy is equal to Vi plus half of I comma j Vij. Okay. This is for, and the first term, this represent the total potential energy of the system. But the second term, this is called the internal potential energy. This term is the internal potential energy of the system. Okay. And this term in the internal potential energy means for example, if you have a rigid body, then let's say these particles cannot move with respect to each other. Okay, the distance between these two particles is fixed, but they can at least rotate. Okay, so that rotation will give rise some internal energy, and that is represented by this term of Vij. So this way you can determine both the kinetic energy and the potential energy for a system of particles. Okay, any question so far on the system of particles? Any question on this one so far, this system of particles? If not, then we'll move to next topic. I'll give you one or two assignment problem from this system of particles. So one problem will be in the last lecture. Someone mentioned that why this term is 0. For example, this term is 0. I'll give you one assignment where you have to specifically show why this term is 0. This term somebody asked in the last lecture why this term is 0. And in the assignment, if you can find out why this is 0, then only you will be able to solve that assignment. Okay. Okay, we'll move on to the next topic of degrees of freedom and the constant of motion. Okay. Okay, this part, yeah. So we'll move to constants. Constants and degrees of freedom. Okay, so let's see. Let's consider that this is a three-dimensional coordinate system. Okay, this is a three-dimensional coordinate system, and we have some particle here of mass m. Okay, so then this mass, in which direction this mass can move? Can you guys tell me? In which direction this mass is allowed to move?
In any direction.
Sir, in all
All
the
the three
three
directions.
directions.
In all the direction, right? In all the direction means it should be there's no restriction. It can move along this direction, it can move along this direction, this any direction.
Yes, sir.
So this should be infinite number of directions is possible, right?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes. But once it moves, how many coordinates you need to represent that movement?
3 coordinate only, sir.
Three.
3.
Yes.
Three. X, Y, Z.
So three coordinates you need basically, right? So basically, let's say mass has moved here, okay, from here to here. So let's say this original position was X, Y, and Z, and the new position is X prime, Y prime, and Z prime. So that is the benefit of coordinate system. That if you know the coordinate system X, Y, Z, then if the mass moves from point, let's say point 1 to point 2, then this coordinate system changes X prime, Y prime, Z prime. So if you know only these three variables, if you know these three variables X, Y, and Z, then you can completely tell the position of the particle in whichever direction it's moved in a three-dimensional space. Okay. Now let's say instead of let's remove this Z direction. Okay. So instead of a 3D space, let's say this particle is moving on this surface of this iPad or this paper. So this is how many dimensions this has, this system? This has two dimensions, right?
Two dimensions.
So
Two
now the
dimensions.
particle can move only along X or Y direction, right? So all we can represent the position 1 and 2 by these two coordinates X and Y. And this new position will be X prime and Y prime. And Z direction, this particle cannot move out of the paper. That is one restriction that we have put in. As we are moving from this to this, so in this first example, there's no restriction. That particle can move any direction. But now in the second case, we put one restriction that this particle will always remain on this particular plane of this paper or this iPad. It cannot move out of the plane. So Z direction is not accessible to this particle, you can say. Now let's remove another dimension as well. So instead of X and Y, now you tell that, okay, we made one road, okay. Let's say this is a road, okay. And this road is along X-axis. And you told that, okay, this is my particle. And so this particle then can move only along this direction because this path is one dimensional now. It cannot move along Y direction. Y direction also now we have removed from its accessible region. So now this particle can move only along X direction. So at any point on this road, so we need only one coordinate. So let's say this is the position 1 and this is the position 2. Okay. So for the position 1, we can represent by X, and in position 2, we need only another variable X prime. So it's only the X coordinate is changing from here to here. So if you see, in the first example, this particle can move any direction, and we needed only 3 coordinates to represent the system. And in the second example, the particle can move only on a plane and we needed two coordinate system. And similarly, and then when we moved from 2 to 3, in case of third, we needed only one coordinate system to represent the particle, and we restricted out this x, y, and z coordinate of the system. So these restrictions that we are imposing on this system, these are called constraint. Okay, this restriction or the conditions. So what is constant? Constraints are basically the conditions, condition or restriction. Conditions or restriction imposed on the motion of the particle. This can be a particle or this can be a system of particles also. On motion of the particles or a system of particles. So these are called constraints. So we don't know what forces is acting, whatever the reason, whatever be the reason. But we only know that in this second example, particle cannot go out of the plane. We don't know the external forces or we don't know anything. But if we only observe the motion of the particle, from that observation, we came to know that this particle cannot move outside or from outside of this plane. Or in the same, in case of example 3, we don't know what are the forces that keeping the particle along the road. But we only know that the particle can move along this road, and so it cannot move along y or z axis. So these forces, so these are basically condition or restrictions. Okay, these are imposed on this motion of this particle, and these are called constraints. Okay, and okay, so let's see another example. So we already discussed about this kind of system of particle. This is x and y. Okay, and let's say this is a rigid body. Okay, rigid body means that if object or a body that you cannot deform. Like generally, if you have a body, if you apply external force, you can deform it. Okay, if it is not a rigid body. For example, if you have a piece of iron or a piece of wood, if you put external forces, it's not easy to deform. Okay, of course, if you put enough sufficient force, you can deform it. You can deform it or you can break it. But in general, in ambient condition, that body is not deformed. So those are called rigid body. But mathematically, how we can represent a rigid body? So rigid body is also a system of particles. Rigid body is also a system of particles, and this is also composed of, let's say, n number of particles. But in case of a rigid body, the distance between these two particles is always remains the same. So let's say this is ith particle and this is jth particle, and that this distance between these two particles will always remain same. So let's say you represent this by Ri and you represent this by Rj. Okay, for a rigid body, Ri minus Rj, this will be a constant. You cannot change it. This will be a constant. Okay, so we don't know whatever force. This may be some molecular force or something, but those forces are keeping the distance between these two particles inside the rigid body constant. So this is also one example of a constant. Okay. This is not present. If you let's say if you have a cylinder, okay, you have a cylinder and there are n number of gas molecules. Let's say these are gas molecules. Okay. So in case of these gas molecules, the distance between two particles, this is not fixed. This can change as the gas particles are moving in any directions. So this distance can be changed. But in case of a rigid body, that distance is fixed. But these gas molecules, they face another kind of constant. Let's say this is a closed cylinder. Okay, this is a closed cylinder, and you are measuring the position of this each gas molecule from the center. Okay, so let's say this is the center. Okay, This is the center. Or let's say this is a sphere to simplify. To simplify, let's say this is a sphere, okay? This is a sphere and you have gas molecule inside this sphere, okay? Now the distance between these gas molecules are not fixed, as I told you. But if you measure the distance of these gas molecules from this center, let's say this origin, so this distance will always be less than the radius of this sphere. Let's say radius of this sphere is a, then the distance of this ith gas molecule, it will always be the less than the distance of this radius of the sphere. So in this case, Ri will always be less than or equal to a. So this is also example of a constraint. Okay, that these gas molecules, that they cannot come outside this closed container. So that is also kind of a constraint. So whatever be the condition or the restriction that we are imposing on this motion of the particles, those are called constraint. And what is degrees of freedom then?
Total number of independent terms in the set.
Degrees of freedom is the independent number of coordinates that you need to represent the system. For example, in this case, what is that? In this case, we needed 3 coordinate system to determine the configuration to position of the particle. So this has 3 degrees of freedom. In the second example, we needed only 2 coordinates to represent the position of the particle. So it has 2 degrees of freedom. So degrees of freedom are basically number of independent coordinates. Okay. So degrees of freedom are the number of independent coordinates required to completely describe or specify the particle or system of particle. This is degrees of freedom. That how many coordinates you need. For example, let's say you have a simple pendulum. You have a simple pendulum, and this simple pendulum is moving along this in this plane of this paper along this line. Okay, and this is, let's say, this is the XY coordinate system. This is X direction, this is Y direction. Okay, let's say pendulum is somewhere here at this point. So how many coordinates would you need to represent this pendulum?
2.
Yes, two is right. Let's say if you know X and Y coordinate, you can tell where is the pendulum. Okay. Any other answer?
Theta, sir.
Theta and
R is the constant now, because length
yes,
of the
so
string is
this
constant.
distance, let's say this distance is R. Okay. So of course, this pendulum you can represent by this XY coordinate system. So in the XY coordinate system, you need 2 independent variables. But if you look carefully, this X and Y coordinate is not independent, because if this length is fixed, length is R, then R will be equal to root over X square plus Y square, right? So R is not, this X and Y are not independent. So if you know X, from this relation you can determine Y. So you need only one coordinate. Only coordinate is theta, because if you know the length, this is basically length R, this is equal to basically length. This is fixed. If length is fixed, there is no change in length. So whenever this pendulum is moving some other position, it's only changing the angle. So you have only 1 degrees of freedom. So let's, DOF means degrees of freedom. Okay. So in this case, you have only 1 degrees of freedom. In this case of simple pendulum. Okay. So let's say in this case, how many degrees of freedom you have? Let's say this is again simple pendulum. but you have two mass. Okay, let's say this is mass m1, and from mass m2 you have another pendulum. Okay, then and this is the xy coordinate system. Then in this case, how many degrees of freedom you have? So for m1, position of the m1 you can represent by, let's say, coordinate x1 and y1, right? This position, let's say x1 and y1. Similarly, mass m2 you can represent x2 and y2. But is there any relation between x1, y1 and x2, y2? If, let's say, these lengths are fixed, L1 and L2, those are fixed.
Yes, sir.
Yes.
How many coordinates you need in this case then?
One.
In this case, let's say this angle is theta.
2, sir.
Yes. So whoever said 2, that is correct. So let's say this is theta 1. This m1 mass has angle theta 1. And if you know from this vertical line what is the angle theta 2, then this will completely specify this system. So you have, again, this case degrees of freedom is 2, theta 1 and theta 2. Okay. So if you have to look this, so these are not unique. Okay, you can represent by other thing as well, but you have to look how many restrictions are there, or how many restriction or conditions are imposed on the motion of the particle, and what are the minimum number of variable you need to completely specify the system, and those are the degrees of freedom. So let's see, you have another example. So let's say this is a sphere. This is a three-dimensional sphere. Okay. This is a three-dimensional sphere, and you keep one mass m here. Okay. So how many degrees of freedom this mass has in this case?
Sir, 1.
Why 1?
Only
Sir,
theta.
sir, if we define x,
So
sir, we have to
let's say,
define only
let me
theta.
completely specify first. So let's say this is the ground. Okay.
So 2
And you
angles
kept one
required,
sphere.
sir.
Now tell me how many degrees of freedom it can have.
So
Sir,
2.
then 2.
Why 2?
Because there is one angle in longitudinal direction and one angle in latitudinal direction.
So yes, so let's say you are talking in spherical polar coordinate. So there you have theta and phi. But I have not told you that this particle always remains on the surface of the sphere. So if this particle slowly comes here, let's say at this position, so it can fall here. So this R can also change in this case.
So then it will 3, sir.
So if this mass is restricted to move only on the surface of the sphere, then your answer is correct, that then DOF is 2. But if this mass can fall, then it will have 3 degrees of freedom. Then you will have 3 degrees of freedom. R, theta, phi, all 3 can change. But what is the constant condition? Does this particle has any constant or not?
Sir, Ri is always greater than or equal to R, sir.
Yes, it has 3 degrees of freedom, but it has one constant, that R square minus A square, let's say A is the radius, that will always be greater than 0. So you impose one restriction, but it still has 3 degrees of freedom. Okay. Let's see another example. Let's see that we have x, y, z coordinate. Okay. This is x, y, and z coordinate, and you have a ball. Okay. This ball is rolling on this xy plane. This ball is rolling on this xy plane. Okay. Then how many degrees of freedom this particle will have? You have a smooth surface. Let's say this is the smooth surface. Okay. This is a very smooth surface, and one ball is rolling on this. One ball is rolling on this smooth surface, and this is, let's say, x. This direction is y, and the vertical direction is z. Okay. Then this ball is rolling on this surface. Then how many degrees of freedom it has? So this ball is restricted on the only on the xy plane.
So 2.
So it will
2.
have 2 degrees of freedom. Okay. Now instead of smooth surface, I told you smooth surface. So let's say this surface is not smooth. This surface is uneven. Okay. There is some uneven surface. And then the ball is rolling. This is y and this is z direction. This z direction. Then how many degrees of freedom this ball will have?
3, sir.
Why 3?
Because it can also goes in the z direction.
Because z
So
coordinate also
in
changes
this case
of
also
center
its
of
degrees of freedom is 2. In this case also its degrees of freedom is 2 because this uneven surface you already know. If I tell you the position of x and y, you will tell what will be the height at the z axis. That is already known.
Yes, sir.
If z is known, that if I tell you go to this particular position and you already know the height at that position, at the xy position. So z coordinates already related to x and y. So that's why this ball will have 2 degrees of freedom. Okay.
Sir, so we can conclude from this कि surface से फर्क नहीं पड़ता है object अगर उसमें है
It
तो
depends. Like if you have a prior equation where you can tell what will be the z coordinate, then we'll have 2 degrees of freedom. But if because of something
So
else
what equation
can
we
go to
have
z
in
axis,
this
then
case?
we'll have 3 degrees of freedom.
So what equation we have?
Equation means whether this position you already know in terms of x and y or not. So let's say this is not predefined. Okay. This is not predefined. So let's say as the ball is moving, suddenly there is some spike on the surface, and because of that the particle moved upward. So clearly in that case you will have 3 degrees of freedom. If this is static, so or I can say if this surface is static, it's not dynamic, then you can tell this is or dynamic or regularly dynamic system, then you can say this is a 2 degrees of freedom again. But if there is sudden spike at the surface and because of that particle move, then it will clearly you need to know at least 3 coordinate to represent the system. So basically how many coordinate you need? Independent coordinate you need. That's why that independent part is very important. Okay. That independent part is very important. How many independent coordinate you have? Okay. 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 So there is also classification of constant. Okay. We'll classification of constants. Okay. So first classification is called holonomic constant. Holonomic. And second one is called non-holonomic. So holonomic means this constant relation, this you can put in terms of some equation. Then this is a holonomic constant. But if you cannot replace this by equation, then this is a non-holonomic constant. For example, this case of sphere that I told you. If you can tell this is r square minus a square, this is equal to 0. So this is a equation. You put this restriction. So this will be a holonomic constant. But if you tell this particle can also fall from the surface, so in that case, the relation is r square greater than or equal to a square. So this will be a non-holonomic constant. Okay. So if you can write down this equation in the form of equation, then this is a holonomic constant. But if you cannot write down the constant relation in the form of equation, then that is a non-holonomic constant. And holonomic has another property. This is independent of velocity. Independent of velocity. This constant relation is independent of velocity. It only depends on the coordinate. That's why it's called holonomic. But in case of non-holonomic, it will depend on velocity. will depend on, or it will have some form of velocity included in the constant relation. So that will call non-holonomic constant. There is another form that is called conservative. Conservative or dissipative. And as you can see from this name, that if the forces are conservative, the forces of constant, those are conservative. Like, and if the forces of constant, those are dissipative, those are also called dissipative constant. Okay. For example, if you have a simple pendulum, here the forces are conservative. So then the constant relation is also conservative. What is the constant relation in this case? Can you guys tell me for the simple pendulum? So in case of simple pendulum, you have this mass mg, that is force acting on in this direction, and it is attached to this rigid support with some tension T, right? So these two are equal. So that is the constant relation here. Okay. But dissipative system, where the forces of constant do some work. For example, if you have this gas cylinder, this cylinder full of gas molecules, okay, and this cylinder can expand or contract, then there will be some work done, and so these type of constant are called dissipative. So third type is called bilateral and unilateral. Bilateral means that they can be expressed in the form of equation again. For example, this rigid body that I told you, that they have relation between these particles in the form of equation. But this unilateral means they are one-sided equation. For example, of this again, this gas molecules, that you are only expressing the position of the particle in terms of the length of the cylinder or the radius of the sphere, where r is always less than a, ri is always less than or equal to a. So this type of constant is called unilateral and bilateral constant.
Sir,
Yes.
can you please explain bilateral and unilateral?
Bilateral means the constant are in the form of a equation. Okay, and they work on both the side. So for example, of this rigid body, this relation between this ith and jth particle, so ri minus rj, that is constant, that works in terms of both the particle, not for the only one particle, right? It is valid for ith as well as the jth particle. And last one is time dependence of the constant relation. So one is called scleronomic constant, and fourth type is called rheonomic constant. So this is independent of time. This is independent of t. These constant relations are independent of time, but here the constant relations depends on time. Depends on time means, so as the time changes, the forces of constant also changes. So these are called rheonomic type of constant. Okay. So you can, this way you can classify the various system. For example, if I tell you what a rigid body, if I tell you have a rigid body, okay, and what are the type of constant, I gave you a rigid body and I asked you that you classify what are the type of constant. So you can, if in case of a rigid body, you can clearly tell this is a holonomic constant because it is in the form of a equation and it does not depend on the velocity. And this is also a conservative rigid body constant, sir. Conservative. This is bilateral, and this is also does not depend on time. So this is scleronomic constant. Okay.
So
But if I tell you a gas container or a gas sphere, okay. So in the case of a sphere of a gas, that is not also holonomic. That is also non-holonomic because the constant relation is in the form of inequality, not in the form of equation. That is dissipative. That is unilateral, this is rheonomic. Yes.
Sir, what is the key difference between bilateral and holonomic?
Bilateral, here we don't consider the velocity. That's why I specifically wrote the velocity part. In case of bilateral, it does not matter whether you include velocity or not. But in case of holonomic, it depends on the velocity. It is independent of velocity. Between these constant relation, velocity is an important factor. But for bilateral, unilateral, here we don't consider the velocity.
Okay, sir.
Sir,
Okay.
can you please repeat the bilateral constant?
We'll discuss
Once again?
tomorrow. Okay, I hurried last part little bit. We'll discuss tomorrow. You have next class. Okay. We'll start again from this section. Okay. Tomorrow. Okay. Let's end here. I have not looked at the time, so it's almost over. Next class is about to start. Let's stop here today. Okay.
Okay.
We'll meet tomorrow.